Okay, everyone, welcome to the official beginning of the presentation part of the Einstein Toolkit workshop for today. Our first speaker is Joshua Faber, who is a professor in the School of Mathematical Sciences at RIT. Joshua?
So hello and good morning, everybody. I'll try to share my screen. Let's see. Hopefully this looks right for everybody.
Yep, that's good.
Perfect. Good morning. This morning, I'm going to talk to everybody about binary initial data, the theory behind it. I'm going to spend most of the time on neutron stars, but also a bit on black holes, which are simpler and kind of help set up a lot of the theory behind the neutron stars in a more straightforward way. Just a couple of warnings as we're getting started. I'm not sure I'm going to take the full 90 minutes. I'd like to think that this is instead just lots of time for questions for this talk. The other thing I need to apologize for in advance, Keynote has a particularly aggressive autocorrect speller or autospell corrector. So there might be a howler or two in the auto-corrected text in the talk. I try to catch as many as I could, but if you see one, I'd like to think that that's why. So with this talk, I just want to talk first about quasi-equilibrium formalisms. How is it that we think about constructing initial data? What are the assumptions that go into initial data for general relativistic simulations? Next, I actually want to talk about binary black hole initial data. In some ways, binary black holes, even though they're particularly numerically challenging to evolve in some ways, the initial data aspects are in some cases more straightforward. I then want to get into binary neutron star initial data. And in closing, I'll discuss a few different code implementations, though this afternoon's talks are going to be, or late morning and afternoon talks, are going to be oriented around actually running Lorraine and using data. So I'll leave some of the details for those, I'm sure. So first basic question, why do we need initial data? GR is a second order hyperbolic scheme. So in order to do a dynamical evolution involving relativity, you need initial data. You need not only basically the space-time metric and initial data for anything contained in that space-time, you also need the first time derivatives of your quantities as well, like a standard second order system. Typically, you would say that that occurs at time equals 0. You also need boundary conditions if you're trying to do a simulation that goes over some kind of finite domain. Boundary conditions are a topic unto themselves, and I don't want to deal with those here. That said, initial data problems are really not typically posed as hyperbolic problems, though I guess there was a talk yesterday that kind of went over some of how that could actually work. Typically, initial data problems are going to be viewed as elliptic equations, and these require all sorts of different techniques, different domain discretizations, just a host of different numerical techniques in order to work. One big difference between most of the initial data work you'll see out there and the typical kind of Einstein toolkit simulations, initial data routines are often not parallelized. In some cases, they're not even clearly parallelizable. These are the kinds of calculations that are typically done still in serial, and there's good reasons for that. If the problem that you're looking at really requires a supercomputer and initial data, there is a decent chance you might be doing it wrong. With initial data, the secret is not just to always try to make it a bigger calculation. There are other ways to get higher accuracy, other than just simply kind of resolving and resolving more and so on. The picture at the bottom is kind of a pretty generic artist's depiction of binary neutron star merger. But I want to point out the frame in the bottom left. That's typically where you'd kind of expect initial data to represent. My point is that if you look at that picture, it's really not that complicated. There's some artist's rendering of gravitational waves. Initial data codes often leave that kind of thing out. They're not always so great at including initial gravitational wave content for a simulation because that's really complicated. The neutron stars themselves at this stage are kind of round. They don't have a ton of detailed features. If you ask yourself, how many true physical degrees of freedom are there that you need to describe this system? The answer will turn out typically to be relatively small, certainly not a number of different parameters to describe the system that would seemingly need to require a supercomputer all the time. So this is kind of the world in which initial data calculations. Yesterday, there was a talk about numerical relativity, including the 3+1 formalism. So I just want to kind of review a couple of the basic ideas. Almost all initial data work certainly takes place in this kind of formalism these days. We're going to foliate our spacetime into slices at different times. And in relativity, there's typically quite a bit of choice in how you actually perform this process. For initial data, we're typically concerned most with the initial time slice. And as we'll get into in a second, the time slice that immediately follows it in some sense. Each slice has an intrinsic 3 metric on it. This is going to be typically called something like gamma sub ij. The extrinsic curvature, it's going to be important. You're going to see the extrinsic curvature come up in many of the equations that you have to deal with in initial data. But I don't want to get into so much the guts of how it's actually calculated. Typically from the initial data side, there are equations that relate the extrinsic curvature in terms of the other variables you're dealing with. And it's rarely the hardest part of the code to deal with. It's often kind of specified by the other variables that are themselves the things you're solving for. In this 3+1 system, we also have the lapse function and the shift vector. The lapse function, that's alpha, is essentially the relationship between the coordinate time and the proper time between two different slices at some position. The shift vector is the other important gauge function. It basically tells you how coordinates evolve from one slice to the other as compared to the local unit normal in the 4-dimensional spacetime. So the lapse function and shift vector are what we would call gauge functions. Quite a bit of the work in numerical relativity went into trying to determine ways to evolve those that led to stable evolutions, particularly for black holes. This is the big breakthrough from about what, 16 years ago now, that when it was kind of determined some ways to really handle those. Initial data is a little bit strange in a sense. Some initial data models are pretty much silent on the gauge functions because they're freely specifiable. Some initial data schemes, as we'll see, actually do end up constructing values for the lapse and the shift. But one thing you should keep in mind throughout this, the values of the lapse and the shift are ultimately choices that you get to make given the coordinate freedom of relativity. Even if an initial data code specifies a given lapse and shift, a dynamical code is not actually obligated in some sense to make use of those values. in the calculation. You can kind of choose your own scheme instead, and the results should come out to be fine. So what is it we're doing when we say that we're solving an initial data configuration? Some equations need to be satisfied, and they are, in a sense, non-negotiable. Initial data, just like numerical evolutions in time, have to satisfy the Hamiltonian and momentum constraints. In fact, when we say we're solving an initial data model, typically a good part of that solution is actually solving the Hamiltonian and momentum constraints in some set of coordinates and variables that we've chosen. We know that these constraints, if they're initially satisfied, should be preserved by the evolution scheme. They have to be completely consistent. There's a great analog that several people have pointed out over the years. If you look at Thomas Baumgartner's work, you'll see him use this as an example to kind of elucidate the role of the physics here, for instance, among others. In electricity and magnetism, the divergence-free nature of the magnetic field basically plays the same role there in a simpler scheme that the Hamiltonian and momentum constraints do for general relativity. Up top on the upper right, you see the divergence-free nature of the magnetic field. This is familiar from basic undergraduate electricity and magnetism. Below it, you see the time evolution equation for the magnetic field. But if you ask yourself, what do you get for the time evolution of the divergence of B, you can take the divergence of that bottom equation, interchange the derivatives, and you'll find that the divergence of the bottom equation gives you the time evolution of the divergence of the magnetic field, and it's equal to, in this case, let's say negative C in what I believe are Gaussian units, times the divergence of the curl of the electric field. But the divergence of a curl is automatically 0. So what you find is that the time derivative of del dot B is also equal to 0 automatically from the equations. If you satisfy the constraints initially, then they're maintained through time. The Hamiltonian momentum constraints basically play this role in numerical relativity. Since this was covered yesterday, I'll just say that a big part of setting up general relativistic evolution schemes has been a process of learning how to evolve the Hamiltonian and momentum constraints over time in a stable way. This underlies quite a bit of the BSSN approach to dynamical evolutions. But in our case, when we deal with the Hamiltonian and momentum constraints, we're going to deal with them at some fixed time. And basically, they're going to be showing up as elliptic equations in initial data schemes. Hamiltonian and momentum constraints are not enough equations to specify the space-time metric and its time derivatives and everything else like that. We typically also need matter and gravitational sources. They could be black holes, which are typically kind of like points in space with gravitational fields. We could have neutron stars, which are extended. We could have accretion disks. We could have any number of different physical situations. Sometimes we might want to specify some kind of electromagnetic fields that live in our spacetime, though this is quite a complicated problem to do in a fully self-consistent manner. We also need some rule that establishes how we're going to construct quasi-equilibrium configurations typically, and the dynamics of our system. Quasi-equilibrium basically means that when we set the system in motion for at least a short amount of time, we typically want it to kind of reproduce itself moving forward for binary orbits, typically with a little bit of spin. And we'll get to that in a second. Ideally, we should be able to model any kind of reasonable physical effect that we want. As we'll see kind of throughout this talk, some physical effects are modeled extremely well. Some in a vaguely approximate manner, but still pretty accurately. Some in a more schematic way. depending on how important things are to get self-consistently versus how important they are just to include in our physics for dynamical simulations. So as I mentioned in the last slide, the big assumption underlying quasi-equilibrium for binary systems especially is typically that what we want them to do is go around in space. We have orbits. Circular orbits are typically assumed, though there are other ways to generate ellipticity. But at least initially, when we place our binary in a circular orbit, the typical assumption at the beginning is that if we go forward some small amount of time, the system will rotate around its axis. But basically in that co-rotating frame, the situation at time equals 0 should look just about exactly the same as the situation at time equals epsilon, where epsilon is some small. The notation that or the nomenclature that you'll come across, if you're not quite so familiar with this, is the language of helical killing vectors. This always sounded kind of violent to me, but killing is a name, not a verb in this case. A killing vector is basically defined so that the metric is invariant. As we move along that killing vector, in proper mathematical language, we want the metric to have 0 Lie derivative as we move along a killing vector. The simplest way to express this is basically that a killing vector will have a time component and an azimuthal component that accounts for the rotation. The metric advances in azimuth as time moves forward. This is a choice that we make for describing initial data. It has several kind of good properties as an assumption. It's actually relatively simple as things go. It typically gives you a circular orbit for your binary components initially, which is what you would typically want. It does have the habit of often leaving out a lot of the gravitational wave content of the space-time. This is sometimes less good. It's not that the gravitational wave content is impossible to include, but that it's something that we typically don't focus on because it is a much harder problem in that sense. This is kind of the standard underlying assumption in order to begin with a circular. The other choice that's made in virtually all the schemes I've ever seen, and this certainly was described yesterday, would be to do a conformal decomposition of the space-time metric. So a conformal decomposition it can be done without loss of generality. What we're going to do is say that our space-time, sorry, let me try that again. What we're going to do is say that our spatial 3 metric can be expressed as some field psi taken to the 4th power times gamma bar ij, where the determinant of gamma bar is equal to 1. In this approach, that field psi would be known as the conformal factor. We haven't made any assumptions yet that break generality. We are going to at some point. There's a couple of different approaches for initial data, both commonly used depending on the problem you're looking at, that make use of this. And I found a typo. Let's see if we can fix it. Oh, nope. I'll fix this later. The conformal transverse traceless approach, which dates back to 1979, requires us essentially to specify 2 components of the spatial metric and their time derivatives. And basically we use constraint equations to determine all of the other quantities. This is the method that underlies Bowen York initial data for black holes. This is the approach that's used in the 2 punctures code for generating the black holes that 2 punctures uses. And it's probably the most widely used of all of the Einstein toolkit's initial data routines. The other approach, and apologies for the typo here, the conformal thin sandwich approach, this is also James York, but this is from 1970, sorry, would be from what's the year? The year would be 1999. I need to check on the year. It's not 1970. Assume I believe it is 1999. Assume some behavior from the metric on neighboring time slices. So conformal thin sandwich data is what you might expect if you want to say that your data is in initially in some kind of quasi-equilibrium mode. I'm going to specify my data at time equals 0, and then kind of require at time equals epsilon, where epsilon is small, that the metric and everything else has evolved in a given way, typically as some kind of rotation along that killing vector. By doing so, if I know my initial metric and how it's behaving at the start, what it does is it specifies the time derivatives, those first derivatives in time of the metric as well. Typically, in some sense, you want to set those initial time derivatives equal to 0 as you move along that killing vector for a slightly more complicated version of 0 than you might otherwise. The conformal thin sandwich approach is the standard approach for neutron star initial data. And in general, if you're talking about quasi-equilibrium configurations, you're more often than not going to be finding yourself using the conformal thin sandwich approach. So with all that done, it's worth talking about binary black holes as a stepping stone on the way to binary neutron stars. And thank you for chat. Yeah, so 1999 for conformal thin sandwich. But it is definitely the same James York Jr. So let's talk about black holes on the way to neutron stars. In a weird way, for initial data, black holes are probably simpler. The main thing that makes black holes easier to deal with, they're vacuum sources. They have no extended matter. The stress energy tensor describing the black hole is basically 0 except at the locations of the singularities. It doesn't extend throughout your computational domain. Black holes also have fewer parameters that we need in order to describe them. They have masses, they have spins, so angular momentum is a vector. They have momenta. Formally, they also have electrical charge, but that's almost always ignored in detail because they are not thought to have any kind of astrophysically significant charge. You can't necessarily tie a magnetic field into your black hole model, though you can certainly put a black hole embedded in some kind of electromagnetic field that in the surrounding material, but that typically requires some kind of matter in order to do. So we have lots of ways to describe individual black holes. We've got the Schwarzschild models, we've got the Kerr solution. We understand black holes in isolation fairly well. What's interesting in some sense is that it's somewhat more difficult to embed those models at times into binaries. So there's often steps done in order to make the process more tractable numerically. It's worth also noting that there's something of a complicated history from the early days of numerical relativity between binary neutron star calculations on the one hand and binary black hole calculations on the other hand. The first full GR simulations performed of merging binaries were binary neutron star calculations. Shibata and Uryu dates back to the year 2000. So this is not the first calculations of binary neutron stars, but the first fully self-consistent general relativistic simulations. Date back to 2000 for neutron stars. In 2005, we had the first kind of stable evolutions of binary black holes. This would be the breakthrough year of Franz Pretorius using generalized harmonic gauge type evolution approaches, followed by Campanelli et al. And Baker et al., who introduced the moving puncture method. After the binary black hole numerical evolutions started to work, there's been quite a movement in the field of binary neutron star simulations, actually following some of the numerical evolution techniques that were pioneered for the black hole simulations. So there was a changeover in many cases in the formalisms used as the neutron star calculations started to look more like the black hole calculations, even though they had been done independently first. The routines that are most commonly used in the Einstein toolkit to calculate either binary black hole initial data or binary neutron star initial data, this would be two punctures and Lorraine, respectively. Both of those predate the existence of the Einstein toolkit. So these routines were around from prior to the Einstein toolkit actually being compiled, collected, and developed. As we get to binary black hole simulations, binary black hole initial data calculations, it's worth noting that there's basically two different ways of going about this. It's a question of punctures versus excision. So black holes have two potential kinds of singularities present. There are things like coordinate singularities. The Schwarzschild metric famously has a coordinate singularity at the horizon, but there's nothing about a coordinate singularity that says that you have to deal with it as such. If you have a Schwarzschild black hole, you can change your coordinates and get rid of the coordinate singularity at the horizon. And in fact, in numerical simulations, this is typically what you'd want to do. There are, however, physical singularities for black holes. These are located in some sense at the center of the black hole. These are basically unavoidable, but they're also extremely troublesome for numerical schemes. Something in the space-time metric is going to be infinite inside the black hole. And if you try to be clever and essentially do 1 over that thing, to basically do 1 over infinity equals 0, you're going to not be smooth at that point. This basically leaves you with two kinds of choices for how you're going to deal with your singularities in practice. One method is excision. You're going to cut out a region around the black hole, inside the black hole, and impose boundary conditions there. You want to cut out a region of space-time inside the horizon and impose boundary conditions on that inner surface. It's absolutely a rule. You have to make sure the excision surface is inside the horizon. So essentially it can be hidden away. The other approach, punctures or moving punctures, is to choose coordinates that have a point-like singularity. That's the puncture. One advantage you have is that rather than deal with the infinity, you either make sure it falls in some sense between your coordinate points, or if you need to, you can kind of modify your field values somewhere inside the horizon to keep things finite. The reason this works is the same in both cases. In both cases, we're going to rely on causality to hide any kind of numerical mumbo jumbo that we're doing. Because of causality in an appropriate evolution scheme, anything that happens inside the horizon stays inside the horizon. It's the Las Vegas of the numerical relativity world. So basically, numerical errors can be kind of hidden inside the black hole horizon. You kind of sweep them up there, and they should not ever recur to cause you problems. So when you're dealing with excision, the question becomes, how do you appropriately set boundary conditions for the black holes in such a way that that any kind of physical assumptions look the same from the outside world? I will say that excision is more widely used in generalized harmonic gauge evolutions, and less so for much of the BSSN work, though there's nothing inherent that says that it has to be exactly like that. In an excision calculation for initial data, boundary conditions have to be applied to that missing region somewhere inside the horizon. Lorraine, for instance, has actually, so Lorraine is an initial data code that's part that's included as an external library for the Einstein toolkit. And it's one of the codes that's been used for binary black holes. It's certainly not the only one, there are many. Lorrain's has used some of the most common boundary condition approaches though, for black holes. The most widely used kind of early excision boundary conditions were from Cook and Pfeiffer. They were constructed in the conformal thin sandwich approach. Basically, you assume that outgoing null rays have zero expansion and shear at the horizon. And you assume that initially your apparent horizons are going to remain at fixed coordinates. If you do so, you get a complete set of boundary conditions, and you can apply them at that spherical surface inside the horizon. And the results are fairly good, except what they found over time was that the angular momentum that you calculate right there at the horizon tends to be a little bit different than what you might otherwise expect. There was a follow-up paper by Caudle et al. With some of the same authors, where you can add some kind of quasi-local measures of spin near the horizon in order to kind of nail down the local idea of how fast the black hole is spinning, and match much better to the physical assumptions that you want to make about those black holes. So both of these are implemented in the Lorraine code, for instance, which is publicly available. This is certainly not the end of the story. People have looked for a while at how you can possibly improve things in Varm et al. From 2018, which is the figures you see on the bottom right here. What you're looking at is the Hamiltonian and momentum constraint total energy for different sets of black hole excision conditions. You'll see the horizon is shown as the yellow circle there. What they found is that using some of these more, I don't want to say old fashioned, but some of these previous excision boundary condition models, there actually is quite a bit of constraint violation that develops. It's largely located inside the horizon. It's trapped there, it cannot get out. But at the same time, you do see large violations as you approach that excision surface, with some numerical leakage in a sense, or some numerical artifacts that do occur outside of the horizons. Using what they call negative expansion boundary conditions, and I'll refer people to the paper there, you can actually limit the constraint violation significantly, both inside and outside of the horizon, all the way up to the excision surface. The most famous black hole solutions, though, for people starting to work on numerical relativistic black hole simulations, would definitely be Bowen York solutions. These are the ones that underlie the moving puncture method. So Bowen York solutions, I'd encourage people to kind of look through any of the derivations. It's one of the few cases where you can kind of work through the math front to back in a way that won't take a particularly long time. It's worth sitting down with the equations and seeing kind of how they were derived and how they work. As a test bed problem, I don't think there's really any better. We're going to assume a conformally flat metric. We're going to assume that gamma bar sub ij is just the metric of flat space-time. So all of the gravitational field is essentially collected into that conformal factor. We're also going to assume maximal slicing. That's an assumption that the trace of the extrinsic curvature is 0. This is more complicated for those who really want to kind of find out about maximal slicing and related issues. That's starting to become the domain of mathematical relativity in important ways. In any case, going back to the Bowen York solutions though, we're going to assume that we can write our extrinsic curvature. Again, that's basically a proxy for the time derivative of the metric. We're going to write it in terms of some kind of vector potential. And that vector potential, when we use the momentum constraint, can be written down. We can write down solutions to the momentum constraint for the vector potential that depend on the momentum and the spin of some point-like object. And you see the formula here, where P is the momentum of the black hole we're choosing, and S is the spin, and X there is just the distance away from the point discontinuity representing the black hole. The beautiful thing about this method is that once we have that vector potential, we can build the extrinsic curvature, and the extrinsic curvature acts as the source term for the Hamiltonian constraint equation you see at the bottom here. And that is an elliptic equation. We can solve for the conformal factor. And we get, as a result, our binary black hole configuration. You could actually get an arbitrary configuration with any number of black holes. Those certainly binaries are the astrophysically most interesting case. One thing that's always struck me, and hopefully people notice this here, this is not, the Bowen York solution for a moving spinning black hole is not equivalent to a Kerr black hole. Kerr black holes are famously not conformally flat. In order to flatten out the metric, what you're actually doing is taking, in some sense, a Kerr black hole and adding in gravitational wave content in order to flatten out the local metric. You're adding in gravitational wave content, just like noise canceling headphones have to, in some sense, add in noise in order to cancel out the ambient medium. So for moving puncture evolutions, this was kind of the recipe that was used widely throughout the field for years after the moving puncture breakthroughs. What you would want to do would be to use something like the two punctures code or a similar kind of code to generate your conformal factor and the extrinsic curvature, since we need to use these inside a numerical evolution scheme. You need to choose the masses and momenta and spins for the black holes, according to some prescription. It's somewhat important, if possible, if at all possible, to always do calculations in the center of mass frame of the binary. It turns out, and this was noted in the original two punctures paper by Ensorg et al., there are logarithmic terms present in the weak field expansion, especially for systems with net linear momentum. The logarithmic terms occur at higher order, essentially. If you have net linear momentum in your system, these end up mucking about in the spectral expansion that you use for these systems, and they can limit the total accuracy of the calculation and force you into requiring higher resolution in order to get results of equivalent accuracy. If you use something like two punctures, you actually do need to specify a lapse and a shift in order to launch a dynamical simulations. You don't really get those from a conformal transverse traceless formalism, but they're gauge freedoms. You're allowed to choose kind of the model that you want. You have to be prepared for your system to evolve and ring down. Because you have spinning black holes potentially plus gravitational radiation, that initial gravitational radiation will go in different directions. Some of it will proceed outward, giving you some of the junk radiation you see typically at the beginning of a gravitational wave train. Some of it will actually be accreted by the black holes, lightly changing their parameters initially during the evolution. As a result, famously, there are spin limits for moving punctures. You can't go above a dimensionless spin of about 0.93 or so. If you try to initially spin the black hole faster, it'll absorb gravitational radiation and actually slow down the spin to the point where something around 0.93 is kind of the spin limit. There are other more complicated approaches that people have developed in order to deal with high spin binary black hole initial data. So I'd encourage anyone who's interested in those kinds of models to read up. The cost is additional numerical complexity, but if you want to study high spin systems, that could easily be worth the effort.
Sorry, may I have a question?
Yes, absolutely.
Thanks. This is about the last thing you said about the spin limit for the Punctures method. I remember like 2 or 3 years ago that there were some studies, I think they were about of Josef Zoklover and PhD student Jan Ruchlin. They developed some modifications of the Punctures code. I think it was called high spin or high speed, something like that. And I tried reading their paper and tried to implement those changes in the Punctures code. I just wanted to know if, as far as you know, there are some plans in the Einstein Toolkit community about implementing such modifications in the Einstein Toolkit public versions in order to perform simulations of even maximally spinning black hole binaries.
Right. So that's a great question. So I should know that Josef Zlotauer has the office next door to mine. So as soon as, especially COVID is over, or at least COVID is on the wane, this will be an easier question to ask because I can walk next door. So Josef Zlotauer and collaborators at RIT, Ian Rucklin and others have been working on, I think they call it high spin ID. Mario Gutierrez Abed is one of the graduate students at RIT, so he just provided the link in chat. Jeffrey Lovelace has also done quite a bit of work on high spinning systems as well. So essentially, just to explain the way that just to explain for everybody, the way you generate higher spins, you have to drop the assumption of conformal flatness. That's unphysical in this case. We know that Kerr black holes are not conformally flat. So if you change your assumptions, and there's still in many ways assumptions about the conformal metric itself, you can definitely get higher spins. I don't know the plans for how different aspects are going to be included in the code releases. Certainly Josef's work is compatible with two punctures. So Josef Zlotauer's work was kind of done with a modified version of two punctures. I forget off the top of my head how Jeffrey Lovelace's, what the underlying code was, but I mean, the mathematics are there for someone to try. I don't know what the release schedule is. As always, the question is always, if it's not out there already, either it will be released kind of as its own, its own thorns at some point, or there's always the outside possibility that Zach Edian or someone in his group will add it to some kind of NERPy scheme at some point and release it publicly that way. When in doubt, either of those is always possible. I don't know the actual time frame, but it's something we could definitely, that could be followed up with in discussion at some point. But I don't know the release timescale for those. The papers are out there, but I don't know about the public code. But yeah, that's a great question.
Thank you very much.
So yeah, on the 2 slides ago, I actually kind of did a bit of a bait and switch on everybody, and I want to apologize for that now. I talked about elliptic equation solvers and just said, oh, you solve an elliptic equation without actually mentioning how you solve an elliptic equation. So elliptic equations, in some sense, all behave something like Poisson equations or Laplace equations, sometimes with some more complicated terms in there, but at heart, that's their underlying structure. One nice thing, and this has been a true help over the years, in general relativity, the elliptic equations you deal with are often much more stable than you might expect. Relativistic corrections have this habit of always making gravitational contributions stronger. Nonlinear gravity is always stronger than linear gravity. As a result, since all the changes tend to go one way, it means that elliptic solvers tend to be more stable than you might otherwise feel entitled to. The problem for initial data is that our interesting problems are almost always not smooth somewhere. There's some place where the fields we're looking at are not infinitely differentiable, and smoothness is baked into a lot of the mathematical models. For black holes, this occurs either at the singularity or the horizon. For a neutron star, you run into non-smooth behavior at the surface of your neutron star, as well as any transition regions inside the neutron star, if those happen to occur. The geometry is not well suited for Cartesian-based codes typically. Not that it can't be tried, but the geometry makes your life harder. I believe Roland is involved in a project actually that has looked at other tricks you can use about exactly these kind of problems. So a lot of the work has gone into clever numerical techniques for these equations. A little bit on why 3D Cartesian grids are hard, just to justify that passage. Again, not impossible, just harder. I'll note 3D Cartesian grids are extremely widely used in numerical relativity, including most of the Einstein toolkit runs ever performed. So why not typically in initial data? Boundary conditions can be tricky for Cartesian grids. It's difficult to get your boundary conditions exactly right at finite distances. Boundary conditions are even a problem for dynamical evolutions to get right. They're a challenge. The lack of smoothness, either because of singularities or neutron star surfaces, typically limits the accuracy you can get if your numerical method does not take that into account. You switch from exponential gains in accuracy down to power law, and that limits the maximum accuracy you can get. I will say mesh refinement solvers, trying to deal with mesh refined grids, are something just of a programming nightmare. It's a hard problem dealing with multiple resolution levels as well as an elliptic problem. The mode decompositions, if you're using that kind of scheme that you would choose in Cartesian coordinates, don't match well with the underlying physics, and that's always a challenge. The shapes are different. Fourier modes are not how you would describe binary neutron stars or binary black holes. In some sense, what you're doing in working on something like mesh refined grids is trying to turn a desktop computing problem into a supercomputing problem. Again, not that it can't be done, but it's a challenge. Again, I'll go back to that initial picture, the NASA cartoon from the beginning of the talk. Binary neutron stars in particular, they're just not so complicated in the right physical variables, as long as you choose the right physical variables. They're two round things separated at a distance. And you're probably sweeping more of the complicated physics under the rug. So why is it that we use spectral methods so widely? Spectral solvers are the workhorses of initial data software. Typically, what you do is you adapt the coordinates to the problem you want to look with. Not so much spherical coordinates typically, but any number of spheroidal coordinate schemes that in some sense match your coordinates to the black holes and neutron stars that you're looking at. Anytime you can match your coordinates to the problem at hand, it tends to simplify the math and improve the accuracy. So spectral methods just mean we're going to expand a function in terms of modes and coefficients. And if you're dealing with modeling smooth functions, you typically get exponential convergence when modeling smooth functions. For every set of mode coefficients that you add, you get the same geometric increase in accuracy and an exponential decrease in coefficient magnitude versus coefficient number. For non-smooth functions, it's power. For better and for worse, it's extremely difficult to supercompute your way to high accuracy when you use spectral methods. If you're using them, then typically for a surprisingly small number of coefficients, either your method works and will be accurate, or there's an underlying flaw and it will never be highly accurate. The secret is typically to work smarter at the problems rather than working harder just using the computer. Just so that we're clear on the language, Fourier decompositions, spherical harmonic decompositions are certainly spectral methods. Chebyshev polynomial fitting is typically done when possible. So this is what I mean kind of by spectral methods, though certainly there's different functions that can be used in the expansion. The problem often turns out to be one of choosing the right coordinates and your domain structure. So why is choosing coordinates such a key thing to do? Well, for black holes, we either have some kind of point-like discontinuity or a spherical surface where we're going to be excising data. For neutron stars, we have a spheroidal boundary where quantities are not infinitely differentiable. In both cases, what you want to do is avoid Gibbs phenomena. Here you see a square wave modeled using Fourier terms, and you'll notice famously that if you have a discontinuous function, as you try to model it with more and more terms, the fit gets better throughout the domain fairly well, except by the discontinuity, where the error never actually drops in magnitude. It drops in width, but it stays at essentially constant magnitude forever. If you have a continuous function, there is a Gibbs phenomenon as well. It causes slow convergence of your coefficients. You need more coefficients than you otherwise would, and the result is less accurate, though it's not quite as graphic as the case of a discontinuity. So the first kind of amazingly clever adaptation for a problem like this, or one of the first amazingly clever adaptations here, would be the two punctures code. So two punctures wants to deal with a grid that you see in the upper left here. That is a grid where your A coordinate goes from 0 to 1 and your B coordinate goes from -1 to 1. The problem is that that doesn't look anything like binary black holes. Binary black holes look a lot more like the lower right, where you've got the two black holes shown as points there, and you've got some coordinates that essentially fill all of space. What they did was come up with a series of coordinate transformations that allow you to smoothly map the upper left grid to the lower right coordinates. For those who are familiar with these, those are not some set of random curves. The picture on the right is the same picture, basically. I stole that from Wikipedia. Those are confocal elliptic hyperbolic coordinates. This is a conformal mapping. That means that if you have an elliptic operator like a Laplacian, in the new coordinates, it will remain diagonal, which makes it a lot more convenient to deal with. What they came up with was a set of conformal transformations that allows you first to compactify the coordinates. There's a number of standard mappings that allow the radial direction or quasi-radial direction. Instead of going from 0 to 1, you can map it to 0 to infinity. And then you kind of, if you can picture it, you take the locations of the black holes and you kind of expand the mapping out at those points. And it gives you a way to kind of map to all of space. In this case, our 2D mapping only covers the half plane, and then there's a phi angle and that allows you to cover all of three-dimensional space. The resulting Laplacian operator, though, will be diagonal in this new coordinate scheme. Not trivial, but certainly can be calculated fairly straightforward. So it involves both compactification, we're letting finite coordinate domains cover an infinite amount of space. And the code basically is set up to do these Chebyshev expansions, which are amazingly good at getting high accuracy results in a small number of coefficients. For those who are interested, and there's a spell checking error. The code uses a preconditioned biconjugate gradient stabilized method. Often trying to work out what that looks like is the hardest part of analyzing the code. Convergence isn't quite spectral because there are logarithmic terms that are just somewhat unavoidable, but it can achieve at least 6th order accuracy for systems, and that can get you extremely high accuracy for a very reasonable number of coefficients. So we're a little over halfway through the talk, and it's about time to actually deal with neutron stars because that was in the title. Don't worry, we will talk about neutron stars. What makes neutron stars different than black holes? Neutron stars have matter in an extended configuration So we're going to have to deal with the stress energy source terms in our constraint equations. They've got pressures and enthalpies that depend on the density or vice versa. Maybe more if we have an equation of state that's complicated. Typically, when you deal with initial data, you're assuming that your neutron stars are cold, whatever that happens to mean. There are no high temperatures to deal with. As you can see in the figures, neutron stars have a tidally extended surface. At that surface, most physical quantities are going to be non-differentiable, but typically continuous at that surface. Initial data does ignore some stuff. We're going to ignore tidal lags that can develop over time as a binary orbits where the front edges lead, sorry, the inner edges lead and the trailing edges trail as you orbit because of accumulated effects. We're definitely not going to discuss forming cusps on the surface of the neutron stars. That's kind of a numerical nightmare. Neutron stars certainly might have electromagnetic fields that thread through them. They also have spins that, while slow, are almost certainly not exactly zero formally. Neutron stars are not exactly rotational. I want to point out though, if you take a look at these three plots, at some level, and these are neutron star initial data, they're fairly simple looking objects. There should be a way to describe these accurately without requiring a supercomputer size worth of numbers in order to describe the situation we're seeing. So let's actually get a little bit into the mess of equations involving solving for neutron stars. Let's start off with matter, because in some ways that's the simplest part to understand. Matter acts like a source term for both the Hamiltonian and momentum constraints. In most initial data schemes, these are combined with the assumption of maximal slicing. That's the trace of the extrinsic curvature 0. And you get something like 5 linked elliptic equations. On the left-hand side, you see the way they're typically presented. This would be for the conformal factor, the shift vector, and some quantity involving the lapse. The right-hand side is the way that Lorraine actually typically solves binary neutron star configurations. Nu and beta are logarithms of the lapse, and then the lapse times conformal factor squared, if I remember right. Ni is their notation for the shift vector. As much as these look different, you'll notice that the lapse and conformal factor typically are these Laplacian type equations that have as their source terms matter. That would be the E and S terms here. Those are linked to the matter field. You have terms involving the extrinsic curvature. Those came up in 2 punctures. And depending on the equations that you've chosen to write down, you might get additional field term derivatives. It essentially has to do with which quantity are you taking the Laplacian of in your solution. All of these can be handled by a typical elliptic solver. Your equation for the shift vector is this other kind of vector Laplacian type operator. You'll notice that it appears in the same way in both of these problems. There are standard numerical tricks for dealing with those as well. That is not any additional complication to speak of, but you will notice that the shift vector solution depends on both the matter source terms as well as its velocity. P is the momentum here. That's essentially a momentum source term. So our source terms involve matter and extrinsic curvature and possibly other field terms. There's many different ways to write it depending on which variables you want to be solving for. One important thing, you generally need the total mass energy and the pressure from the stress energy tensor when you're solving these equations. You can't do it from one hydro or thermodynamic variable alone. You need the full set. The equations are linked. They're not linear, but they really are well behaved. Most elliptic solvers that solve these using relaxation techniques should be stable for configurations. The elliptic solver is often, in weird ways, the least of your problems. Let's talk about neutron surfaces. Those are kind of a key thing for dealing with. The source terms are generally continuous, things like the density, but they're typically not differentiable at the surface of the neutron star. The density comes into 0 and then stops. There's no more density. If this occurs in the interior of some domain, your field terms will be twice differentiable, but you're never going to get spectral convergence for things that are not infinitely differentiable. What you typically want to do is deform your coordinates to achieve higher accuracy. I want to wrap some kind of coordinate line around the neutron star so that they match up and the neutron star surface occurs at some kind of domain boundary that I can impose. That's why you typically would say that the coordinates are spheroidal rather than spherical. The price you pay, and this is where a lot of the work is gone, is that if you start adapting your coordinates for your situation, it changes the elliptic operators and you have to handle the math, ideally in a way where you don't have to code it by hand, where the code's internal workings can handle the modification of the equations themselves. Again, if you form cusps at the inner edge of the neutron stars as they face each other, the mappings essentially will start to die on you. The equations can get very singular in a hurry. That's typically past the point where you really should be using an initial data scheme. You should let dynamics evolve to the cusp. Neutron stars have matter. In some ways, that's unfortunate. It makes them more interesting, but it makes them harder to model. You always need an equation of state for your neutron star that links things like the density, the internal energy of the fluid, the enthalpy, the pressure. In practice, these are not all freely chosen variables. They're linked to each other. The enthalpy depends on the energy and the pressure and the density. And thermodynamics still holds. There is essentially the first law of thermodynamics that has to be treated consistently in the equation of state you're trying to model. Now, you might notice that there's no temperature anywhere in that equation. We largely ignore temperatures in the initial data world. Prior to mergers, there's basically been at least millions of years for your neutron star to just kind of settle down. And typically you don't assume any kind of heating sources that are going to have large effects anytime as your in spirals happen. Even if you assume there's some kind of non-trivial temperature dependence in the neutron star, if you can write it as a function of the density, you can just fold it into the equation of state that way without having to deal with it in its own right. One strange thing, and this has pretty much been true forever, no one really knows what the true nuclear matter equation of state is. What you end up with is a strange situation where there's many different models, each of which is highly precise, all of which have unknown accuracy. So we live in a world when it comes to equations of state of extremely high precision with totally unknown accuracy. They differ from each other way more than the precision limits would indicate. You can always ask yourself in this case, how much precision is needed when you have no idea where the actual numbers are? I'll leave that open to people to determine. One important thing that you're also not going to hear again after this slide. Neutron stars are expected to have crusts. They lead to all sorts of interesting observational effects, glitches, and all sorts of other physical effects that radio astronomers love. We're largely going to ignore crusts to the extent that they're not fluid in nature. We're going to assume that neutron stars are fluid throughout and try to ignore effects like surface tension or any other physical changes that would occur because of phase transitions in your neutron star fluid. Given all of these equations of state, physically speaking, how do we model them? This is so far the best worked part of initial data so far. The ways of treating these are largely enough to handle any kind of situation that we can easily imagine. Polytropes are always the way people like to start, but they're probably not correct. Polytropes are where the pressure is just a power law dependence on the density. There's many tabulated equations of state models out there. In some sense, they typically contain too much information because they're needed for dynamical calculations. A full equation of state will talk about how the energy and pressure depend on the density and the internal energy and the temperature. We're typically going to want to just make an assumption about the temperature, or maybe T depends on rho, and take a slice through our initial data model that kind of ignores that dependence so we can just get the pressure out. as an intermediate ground, piecewise polytropes are often much simpler to use to approximate tabulated equations of state. You basically get a situation like you see in the upper right here, where for pressure as a function of density, you just assume that it follows one power law model until a transition point where it follows a different power law index, and you impose a number of transitions throughout. These piecewise polytrope approximations are good enough to basically reproduce neutron star models fairly well. What you see on the lower right is tabulated equations of state for isolated neutron stars against piecewise polytrope approximations to them. And what you tend to see is extremely good qualitative agreement and typically fairly good quantitative agreement between an equation of state model and its piecewise polytrope approximation. I will say that sharp edges, when you transition from one state to another, are probably less than ideal. There are other numerical techniques that could be used to soften and smooth the edges between one domain and another, though they're not so widely used, in all honesty. The enthalpy, so this is essentially the mass energy plus the pressure divided by the rest mass density. That's often the important quantity that shows up in equations. Enthalpy, we've solved for the fields on a previous slide, but matter was only being used as a source there. There has to be feedback that tells the matter where to locate itself. So you can relate the enthalpy to field values. Here, n would be the Laplace function that we just solved for. Gamma and gamma 0 are Lorentz related factors that have to do with the velocity and rotation state. This is taken from the Lorraine code paper. And essentially we can relate the enthalpy to these other parameters and set the whole result equal to some constant. That's nice. It tells you essentially, given the other configurations, kind of up to that determining that constant, how the enthalpy of the neutron star reacts to the local field and assumed rotation structure. For co-rotating configurations, at ones where the rotation is locked to the orbital velocity, this is actually somewhat straightforward. For irrotational configurations, it's much more complicated. I still shudder every time I see this equation. This is an equation for the velocity potential in Lorraine. That equation, I think, is fairly described as somewhat less than pleasant in order to construct. It involves the enthalpy and all of the different field quantities and all sorts of other terms. This is often for irrotational configurations, the hard step, relating the enthalpy and the velocity of the fluid to all the different fields to make sure everything is consistent. One issue is that irrotational neutron stars may or may not do what you would expect. Irrotational neutron stars are not defined so that they move like solid bodies. They're not just completely backspinning in a way that they are merely translating locally in space. They're defined to have zero vorticity, which is a slightly different condition than, in some sense, solid body rotation. The important thing from this first equation, by the way, is that there's this arbitrary constant we need to set. That's essentially how you adapt the central enthalpy of a neutron star, typically in order to match up with a given total mass. What you do in initial data is typically you want a neutron star of a given baryon mass or a given total mass. So you have to choose that constant in order to reproduce a matter field that yields that total. A little bit more about spins. Neutron stars are expected to be nearly irrotational in the inertial frame. They do spin fast, but the orbital angular velocity as you're coming up on merger is also very fast. At first, people constructed co-rotating models because they're the easiest, but they're simply unphysical. Irrotational models have been widely used. They're the most common assumption about how the neutron stars are moving. But neutron stars do spin. A lot of the leading work on adding spins has been by Wolfgang Tichy and collaborators. So I'd encourage anyone to read some of his papers to discuss how to add in spins. They've come up with a scheme called the constant rotational velocity formulation that essentially adds some kind of more solid body spin. Oh, did I get a coronating? I got a coronating. Oh wait, is it on the last slide? Sorry, yeah. My Mac does not believe co-rotating is a word. So Tichy et al. Basically came up with a way to kind of impose a small rotational velocity on the neutron stars, and then essentially came up with the scheme to solve the rest of the equations in this, and are able to generate not just intermediate spins between irrotational states and co-rotating ones, but also arbitrary misaligned spins as well. And given how much of binary neutron star mergers involves the outer layers immediately doing interesting hydrodynamic and thermodynamic and nuclear things after the merger, certainly adding in vertical components of motion and precession into orbits is the kind of thing that could have significant physical effects. One thing that many people are interested in would be including magnetic fields in binary neutron star mergers. Magnetic fields typically, prior to merger, shouldn't affect the stress energy tensor so significantly prior to the merger. For the neutron stars before the merger, what you're looking at is what is the ratio of magnetic pressure to fluid pressure, and trying to work out, does that magnetic pressure significantly affect the structure of the neutron star itself? Typically, the answer is not quite. It's the magnetic pressure is measurable, but so small that it would only be perturbative for the structure of the neutron stars. As long as it's largely at the perturbative level, you can add in a magnetic field to your neutron stars in some kind of post hoc way where the magnetic field is just imposed on top of the existing hydrodynamic structure in order to come up with a magnetohydrodynamic configuration. The model you see here has been used widely across multiple groups. This basically gives you a, let me get this right, colloidal field. I hope that's right. Located in the interior of your neutron star, where it looks kind of like a little bar magnet living inside the neutron star. This cut pressure is used to kind of keep everything trapped inside the neutron star until things evolve and the merger begins. I forgot the sourcing on that picture. That picture in the upper right is from Bruno Giacomatto. Initial data for generic magnetic field configurations has now been generated for single neutron stars. The formalisms are pretty seriously under development for generating more self-consistent magnetic field configurations, but they haven't quite appeared in the binary initial data to speak of as of yet, where things are completely self-consistently for the magnetohydrodynamic state. So far we've talked about how two punctures work. It's worth talking about how Lorraine works, since people are going to get a chance to try it out later this afternoon. Lorraine has long been the publicly available code for constructing quasi-equilibrium binary initial data configurations, particularly neutron stars. It uses a multi-domain spectral methods approach. So this figure is taken from their original paper. This figure's always been somewhat misleading, but I can understand because of the graphics. What you see is a set of two domains, each of which is ostensibly centered on a neutron star. You should expect that the neutron star lives inside that innermost domain in each case. What they're not showing, probably because color printing was a lot more expensive 20 years ago in journals, is that each of those sets of domains extends through all of space. Each of the neutron stars is surrounded by a full set of domains and each set of domains fills all of space. The outermost domain uses one of these compactified coordinates to extend to r goes to infinity. So every single point in space finds itself both in the set of domains surrounding star 1 with a given set of coordinates with respect to star 1, as well as inside the set of domains surrounding star 2 with a given set of coordinates relative to star 2. So every point in space lives in both the domains around star 1 and the domains around star 2. Both sets fill space. Every single field quantity we're interested in, here it's the ones that show up in the elliptic equations, but it could be kind of any quantity, is broken into a piece that we attribute to star 1 and a piece we attribute to star 2. A lot of the work in the spectral expansion is actually taking quantities known around star 1 and working out what the value is at a given point with respect to star 2's coordinates and vice versa. That's these arrow type things that you see there. But each field is split into a contribution from star 1 and a contribution from star 2. The elliptic equations are actually solved twice. Once for star 1 with all of its source terms, and once for star 2 with all of its source terms. Every equation has to be broken into two pieces, and each star gets a component. Ideally, you want to maximize how many of star 1's kind of pieces are located in the star itself or nearby. You don't want significant source contributions from far out if you can avoid it. You want to kind of concentrate them on the two different stars for maximal mathematical efficiency. But this breakdown into two stars, multi-domains, is the secret to the Lorraine method. What does it look like to do a Lorraine step? It's more complicated than you might otherwise expect. The first step is actually something that you wouldn't think of from a Newtonian calculation necessarily at all. The first step in a Lorraine calculation is determine the angular velocity of the system and the system rotation axis point. You need this in order to set the velocity fields, which control the source terms for the other equations. This is a root finding step. It doesn't actually relax well. You can't kind of go halfway to a solution of a 2D root finding problem. I cannot begin to say how often this particular step, even though it looks pretty innocuous, is the one that causes instabilities in Lorraine evolutions. Their approach, which basically just tries to figure out the right angular velocity and axis in order to locate the centers of the stars at the right point, is surprisingly where a lot of the issues with actually running Lorraine in practice happen. If there was one thing that could be kind of fixing this whole approach to come up with some other numerical scheme to calculate these could actually solve a lot of heartache and headache at times. Once you've got the angular velocity and the rotation axis, you can then establish what the velocity potential should look like, calculate your enthalpy. And once you know the enthalpy, you know where the matter is. You can adapt the shape of the inner domain of your coordinates to the stellar surface itself. The innermost surfaces can deform in order to be more spheroidal than spherical. Once you have your coordinates and you have your matter, you can solve the field configurations. You can determine the space-time metric. And then you start over again and you kind of keep refining the values again and again because these are nonlinear equations. After a certain number of steps, you start adapting the central enthalpy to yield the proper baryon mass. You creep in on the proper baryon mass for your neutron star. You don't want to do it too roughly or you'll take too discrete a step from step to step, and that would itself lead to instability. There are many other codes out there. I would be remiss if I didn't mention them. A lot of work has gone into these. COCAL is the code used by Uryu et al., also people from the Illinois group and others. It's a multi-patch code. It uses kind of interesting Green's functions techniques in order to determine binary initial data. On the right, in both figures, you see plots from the S-grid code. This is, again, Wolfgang Tichy et al. As you can see, it uses multiple patches. This is the code that can handle arbitrary spinning neutron stars so far. I would say, if you look at the upper right, what you see is a surface matched to the neutron star matter, as well as a single, it's multi-patch, but a single domain in practice. If you eventually want to avoid Gibbs phenomenon errors to the extent humanly possible, this is probably the right approach to take. The only non-smooth behavior occurs at a well-defined domain boundary, and that is the one point where you cannot introduce Gibbs errors if you handle the mathematics correctly. So this kind of approach is probably the one that you'd want to use if you were given your own choice. There's also the spells code. Again, this is the kind of multi-patch code. This is used by the SXS collaboration, Caltech and Cornell and others. It was written by Foucault et al. One important thing, it would certainly help if more codes were public and easily available. It's awfully hard to talk about the internal workings of a code when it's not public, because you really don't get to kind of see into the guts of the mathematics to see how it works and tinker. Even Lorraine, which is a public code and has been for decades now, actually responds well to tinkering with various quantities in order to make it work better. So ideally, since initial data codes don't always generate the same excitement as the dynamical results, it's necessary, but rarely quite as exciting, since you don't get to crash anything together. Certainly, the more codes that are made public, the better. I know somebody yesterday talked about kind of various elliptic solvers in NURPy and things like that too. The more we can get out there publicly, the more that I think it'll help advance developments in this field and allow the dynamical evolution calculations to cover new and more exciting parts of the parameter space, as well as adding in new physics and really expanding the calculation of simulations out there. Initial data, it's not that it's not interesting in itself, but in the end, it's a tool. And the more kind of things you have in your toolbox, the better the final product that will be out there. So in summary, hopefully I've convinced you elliptic solvers work very differently than the hyperbolic evolution schemes that you saw yesterday. Some physics and really equations of state are kind of now in this domain are basically easy to implement in initial data. That's been pretty well understood now. Some physics, spins, magnetic fields, it's more complicated because really formulating and solving the quasi-equilibrium set of equations is challenging. These are still often done in a kind of a post hoc way, not fully self-consistent, but honestly, as long as it's perturbative, it's unlikely to be the biggest problem that you're facing. Lorraine certainly remains the most commonly used publicly available solver at present. It's out there. We're involved at RIT in a project to add some documentation and allow more people to use it. We're also, we've got an initial, I forgot a slide on this. We've got an initial data library that we're trying to release to people to, so that you can both, use data that's already been generated, as well as in fairly short order, generate your own if you want to try different parameters or different equations of state or who knows what. In the long run, I really suspect that these multi-patch approaches probably will be the most accurate. They really do handle the surface effects the most naturally. And oh yeah, so there is the kata solver as well. I did forget that one, apologies. These solvers are out there. Some are public, some are not. There is a lot of work to be done to make these the best tool possible. And that's basically about it.
Thanks, Josh.
Oh, so I do have one question in chat if you want me to start there.
Yes, that would be nice.
So the upper right plot looks like a Mobius transformation of an exponential function with the radical axis cut out. I don't actually remember exactly what transformation they're using here. So if I understand this right, what you see in the upper right looks like, I need to read the details to remember it more. What you're probably looking at is something like 4 patches in the plot there. In all honesty, there's a couple of different things that you need to look at here. One is that you definitely want your stellar boundary to match up with some kind of coordinate domain boundary. That's this A = 0 curve that you see here. That's ideal because that is the one place for neutron stars where things aren't smooth. One problem for Lorraine, and I mean, it's been remarked on, but it's a little bit it's a little bit underplayed. One issue for Lorraine is that because it's a multi-domain spectral method, the surface of one neutron star occurs in the middle of the domain as seen by the other star. That will introduce some loss of accuracy inherently in the problem. That's why the source terms are designed to kind of keep that as small as possible. You're not going to see the matter sources from the other star. Those are kept each star to itself. But the field values we said are only twice differentiable there. So when the field values enter the source terms in a multi-domain method, you get some degree of non-differentiability when you encounter the edge of the other star. Single or multi-patch methods should be able to fix a lot of that. I don't remember exactly what coordinate transformation they use. Past that point, it's a matter of resolving things properly. You want to resolve as you go to infinity in a way that walks things smoothly to the boundary. And beyond that point, it's a matter of how do you get the best accuracy given whatever resolution you have. These problems are all typically single machine, not parallelized in a lot of cases. So they're still pretty fast compared to dynamical simulations. You can throw a lot of resolution at them, to accomplish this.
Hi, can I ask a question?
Absolutely.
Related to the question of binary neutron stars initial data, there is the question of mixed binaries initial data.
Yes.
And I was wondering, because there's no publicly available form for Einstein toolkit, even though there are for binary neutron stars or binary black holes. And
right.
What is there any reason for this, or can we create realistic mixed binaries initial data?
So
are there any specific difficulties, or?
This is a really great question. There's, as far as I understand it, there's no conceptual difficulties for black hole neutron star initial data that don't occur in either neutron stars or black holes. It's not easier than those two, but it's not harder than either of them individually. The same issues that would occur for the black hole occur in binary black hole initial data. The same issues that might occur for the neutron star occur when you're trying to model binary neutron stars. So there's no added difficulties from mixing the binaries. If you have a code that can do both already, it should be perfectly well set up to do a mixed binary, pretty much using the existing techniques. Some of the challenges, if I could go back, sorry. Okay. If I go back, the first step here is let's say that we wanted to do this in Lorraine, though this would be generic for any code. The first step would take some thinking about. Lorraine determines the angular velocity and the system rotation axis. by making sure that the centers of the star are located at the right points, where the centers of the star are kind of where it's going to attribute the maximum enthalpy within the star. If you have a mixed binary, that will work for one half of it, but not the other. Typically with binary black hole calculations, you do it by kind of specifying the center of mass positions and momenta and things like that too. So in theory, you'd need to kind of come up with a different prescription for determining these two scalar quantities. These are not fields, these are scalar quantities. You need an equation that tells you the value of omega that you're going to use and where you're going to put the center of rotation. That is entirely feasible. It's just, you know, a different set of equations you want to run it through. Everything else past that point would either be using a black hole solver or a neutron star solver if this was Lorraine. To finally answer your question, because I've been dancing around it, no, there shouldn't be any additional difficulties. Some of the codes out there can already do this in combination. Bruno Giacomazzo in comments mentioned, I did forget one code, and apologies for that. Cutoff is a code that came out, it's from some of the same people who've worked on Lorraine as well. The website there is the same Paris Meudon Observatory that hosts the Lorraine code too. If you can do black hole, and neutron star, you can pretty much do black hole, neutron star. It's just initial data codes haven't always been made public, and work on them hasn't always been as enticing as it has been on dynamical simulations. By the time you get to mixed binary, it's that problem compounded with itself. It's not that it's harder, it's just that you need to get enough people working on it and getting the codes out there and to the public that with documentation that people can use them. So no inherent difficulty, it's all practical.
Okay, thanks very much.
So another problem that's a bit tedious is eccentricity reduction and very unequal mass ratios. Can you summarize a bit the recent developments, in particular with Lorraine?
I wish I could. I'm not sure I can. Let's see. So unequal mass ratios, are you thinking which cases?
Oh, just that typically if you try to crank up the mass ratio in Lorraine at some point, it doesn't converge anymore unless you go to large separations, and that is then very costly. So this is still a problem, I guess. Gotcha.
So yeah, so for unequal mass ratios with Lorraine, some of that's a bug. There is a bug in some of the Lorraine code for their solvers where, again, it's this first point, oddly enough. A lot of unequal mass ratio cases actually fail at this first step. That can in some ways be avoided. Lorraine is an awkward relaxation scheme. Its relaxation scheme is not easy to slow down properly. It has too many different knobs. It doesn't allow you to kind of take small steps properly at times to go from one configuration to the next as you approach the equilibrium that you want. So yeah, a lot of work with Lorraine is to kind of make it go gradually to a state with highly unequal masses, or you name it. There are ways to either play with the code. Again, this first 2x2 root finding solve could fix a lot of problems. We think we've cured many of the problems with unequal masses. I don't remember quite how far we've been able to push it, but getting closer to something like at least 1.5 to 1, if not farther. For eccentricity, I don't know as much about that with Lorraine developments. Are we talking neutron stars or black holes?
Both, I guess. I mean, currently one has to do this iterative procedure of first evolving, measuring the eccentricity, and then applying some ad hoc correction on the initial data. But of course, one could try to get corrections from post-Newtonian methods inside the initial data from the start. So I think I've seen some articles like that. But
30 seconds.
I guess I'd say when it comes to yeah, fixing initial eccentricity with Lorraine, I would be more tempted to ask you rather than have you ask me. For better or for worse.
Fair enough.
Can I have one last question?
Sure. But I'm not in charge of that.
A curiosity, and it doesn't have really to do with what you said, but I'm seizing the occasion. If I wanted within the Einstein toolkit to initialize a binary of black holes in any given analytical metric, keeping them at a fixed distance, and blend the binary by hand in order to you know, relax the matter data. Is there, as far as you know, a way to do this without adopting, you know, the puncture methods or anything like that?
Not really. So Lorraine is really set up most easily for just 2 Cook-Pfeiffer black holes. There is some code to do the caudal excision black holes as well. I don't believe that they actually have the puncture. You can write your own Lorraine thorns to do puncture black holes. I've actually done that. It's not so complicated. It's not perfect for a couple of reasons that involve some technicalities. But I think the quick answer, yeah, if you want to change the assumptions there, you're probably going to be writing some of your own code for Lorraine. You know, that it's not as flexible as one of these code generation codes, something like NURPy, where, you know, it's not built to put in new equations. It can handle it, but you have to write them.
Okay, thanks.